Okay, I like long titles. Don't worry, the title tells you everything about the paper, but you understand the title at the end. So let me just dive in. This is work with PhD student Shamin at the ANU. Harold, so he was a postdoc with me at Toronto. He's now a faculty at NUS, and me last. Okay, so you give me a very complex hybrid, so by hybrid mixed discrete continuous, stochastic planning problem. And furthermore, you say there are unknown parameters, right? That's the problem. Now, there are things that I want to do with this. I might want to do inverse RL in a multi-objective domain. So you have multiple objectives you could be optimizing. I observe your behavior, and you ask me, well, what is the weight of each of your objectives, right? I want to figure out that observing your behavior. This is one aspect of decision analysis I want to address. I can look at infection models. So I have the flu, I cough, I get Florent the flu. Tomorrow, Florent wakes up, gives everyone else the flu, right? Who should get the flu shot, right? Now, I don't know the infection rate. I don't have the flu, by the way. You often don't know the infection rate, right? And you kind of want to know what's the optimal immunization rate sort of as a function of the infection rate. I don't want some sort of local optimum. I want the full symbolic view of how the optimal policy varies as a function of the infection rate. Finally, in trading, you have $1 billion. You want to sell all you have $1 billion of stock. You want to sell it all, but you don't want to sell it all at once because you might affect your other stock if you don't want to sell it all. So in finance, they often look at how much, what fraction of your stock should you trade over time to minimize price impact, maximize your value. What's the sensitivity of your payoff to the parameters of how much you trade? Okay. So you have all these unknown thetas, right? They can be parts of the policy. They can be parts of the parameters of the domain. We want to do these different types of decision analysis. For this last one, sensitivity analysis, you might know often that people look at the Pareto front. You know, they sample different parameters. They say, okay, you know, for all the trade-offs, what's the best thing that you can do? In all of this talk, I don't want to sample. That's expensive. I don't want to do local policy gradients. I really want to take a symbolic, globally optimal view. Okay, and the key insight, there's not a whole lot new in this paper other than saying, hey, there are these cool tools out there and we can put them together in ways that no one's considered before. So the first tool is symbolic dynamic programming. And this allows us to give exact solutions to these really ugly mixed discrete continuous nonlinear hybrid MDPs. Okay? And they really can solve for the value function policy as a function of these unknown parameters theta. Okay? Add to this the fact that we now have, you know, great symbolic algebra tools and Mathematica and Python, all sorts of libraries. We also have global nonlinear optimization. So there's tools like dReal. If you give them a symbolic function, they will come back after some time and say, here's the optimum of this function. It's nonlinear, it's non-convex. Here's the optimum, and this is guaranteed to be optimum. I mean, these tools have only come about in the past few years, but they now exist. They don't optimize 20-dimensional functions, but often you might only have one or two parameters you want to optimize. You can optimize these functions. So we have ways to derive symbolic solutions. We now have these symbolic global optimization tools. And the only point of this talk is to say, how can I put these together and do cool things, right? And the insight is I can do all this decision analysis I just talked about, policy optimization, sensitivity analysis, inverse reward learning or objective learning. I can do it all with these tools. I just want to give you, for those of you who don't know symbolic dynamic programming, I just wanted to tell you what it does, but I'm not going to tell you how it works, just what it does. Okay, and the whole idea is when you're solving these problems, think like Mathematica. You're working with symbolic functions, not like MATLAB, where you're working with sort of sampled vectors. Okay, and the whole idea is in an MDP, if I represent my reward, and therefore my initial value function, V0, and my transition parameters, if these are all just functions, I'm just going to do all my operations of the Bell and backup symbolically. Right? I can multiply them, I can integrate them, I can maximize, actually. Gives you piecewise functions. I can add the reward. So if I start with my t+1 sort of horizon problem, with my t horizon or t+1 steps to go, I can figure out how to act with t steps to go, or vice versa. These are all symbolic functions of the unknowns, like the state x. So just to give you an illustration, here's a robot. It can move an arbitrary continuous amount y along sort of the x-axis. So I can give you this sort of v0, which is the reward, which says basically if you're between -2 and 2, you get this quadratic reward. I allow the robot to move up to 10 units at every time step. So if I'm one step back from the reward, I can get this value. So I only get the reward once, so that's why you get these dips here. But anywhere from 10 down, I can get the maximum reward, and 12 to 2, I can sort of get the edges of the quadratic, right? If I go 2 steps back, I can now move 20, I get this reward. These are symbolic functions. The solution, now one thing is you can't just literally plug this into Mathematica, right? It doesn't really support these piecewise functions efficiently. So it took many, many years to develop the solutions that actually would do this SDP, symbolic dynamic programming, efficiently. And one key idea in the solution was to have this data structure called an extended algebraic decision diagram, which is basically like a decision tree with reconvergent branches. But just quickly, if you look at this, if you just follow the decisions, it'll give you the description of this function, right? The leaves decision are inequalities. They give you pieces, and the leaves are the function values. And in parentheses, I've shown the policy, which you can also derive symbolically. And interestingly, it says, when you can get reward, the action y is just the negative x. If you're at 8 here, then you want to move y equals -8, right? So the optimal policy is y equals -x. Derives this all symbolically, right? Okay. This is all previous work. The key work was done in UAI 11 and IIII 2012, and there is code for this online. Doesn't solve super large problems, but it does do this. Okay, so now we're doing decision analysis. We have these unknown parameters. What's the infection rate of my infection model? Right? So I should point out, this works for nonlinear problems. So now we have these unknown parameters theta, right? How does this affect SDP? Well, it really doesn't. The thetas don't change. I just sort of now derive all my functions as a symbolic function of theta, right? Okay, so just nothing new here, but we can do it. We can solve for value and policy as a function of theta. Okay? So that's what we do, and then next step is symbolically analyze it. What can we do with it? And so I think this is the cool part, like things we could do that we could not do before. So inverse multi-objective learning. So I have a robot that moves again in 1D, but this time it has two objectives. One objective is to get to a goal, say beyond x greater than or equal to 10. And I'm going to weight the objective with weight 1. Okay? The other objective says I have a movement cost, right? Okay? So and that's going to be weight 2. Okay? Now I don't know what your weights are. I don't know weights for a problem, but I will observe some behavior perhaps. Anyway, I can solve for the value as a function of location W. So I fix W1. You don't need W1. You just need W2 to trade off between objective 1 and objective 2. I can solve for the value function as a function of the location W2. And what you see basically is that once the weight is sufficiently low, so going towards 0 here, then for lower locations further from the goal, you'll start to move. Once the weight's sufficiently high, the agent says, I'm not going to move because the cost I'm going to pay for moving is going to outweigh the cost that I would get for getting to the goal. So you can symbolically derive the solution. If I observe now for the multi-objective learning, I observe the agent moving to the right for increasing x between 0 and 10, right? I can sort of use dReal to say, well, what's the maximizing weight 2 as a function of different starting locations, right? And this is the answer you get. So it wasn't moving from negative 20 to 0. That could have meant that the maximum weight was quite high. But if it was moving from 0 to 10, the weight has to be lower to explain the fact that it would move. Okay? So you can sort of now infer what the agent's weights of the objectives are given their behavior optimally. Right? This is a nonlinear optimization problem, but we have tools like dReal that solve it. Okay, another problem. So for epidemic models, there's a model commonly used called the SIR infection model. You would immunize a population fraction nu. The infection spreads at rate beta and has an infection period lambda. I infect Florent today. He's infective tomorrow. Right? Sorry, Florent. Okay, I can again solve for the value function as a function of nu, which is my sort of policy parameter, how many people do I inoculate or immunize, and beta, the infection rate. This is kind of a cool result if you, it takes a little while to stare at these functions, but if you stare at them for a long time, you see some interesting results. So if the infection rate is high, 0.81, then you're going to see the optimal nu is over here at 1. I need to immunize. The infection rate is very high. I need to immunize everyone. Otherwise, everyone's going to get infected. But as the beta, as the infection rate goes lower towards this end, you see that actually if I took the argmax over nu, it's going to actually be optimal at 0. Okay? And I can actually do this analysis directly with dReal. What's the argmax over the immunization fraction as a subject to the infection rate beta, and you get this very simple result that's very explainable if you know SIR models. You know SIR models have this thing called the epidemic threshold. If the infection rate's below some level, the infection just dies out. If the infection rate's above some level, you have an epidemic. That's why it's called the epidemic threshold. And symbolically, without knowing anything about SIR models, this system found, look, if you're below this, if you're below beta equals 0.28, don't immunize. It's going to die out, right? Don't pay for your flu vaccine, right? But above 0.28, you better immunize if you want to maximize the value. Okay, and you might say, well, we've known this result since the 20s, right? Big deal. I say, we've known this result for a few SIR models, right? But if you suddenly insert a log, an exponential, a cube in it, what's the epidemic threshold for that model? We don't know. But I can symbolically solve for the value function. I can use dReal to optimize it. For any model that we don't know how to analytically analyze, we now have these tools that can find what's the best policy, where's the epidemic threshold, right? Things we could not do before. 5 minutes? Yeah, good. Okay, and finally, the last example is trade execution. Again, you've got $1 billion, and maybe you have $2 billion in the company, right? You want to trade $1 billion of it, right? But you don't want to impact your other value of that stock. How much fraction theta of your inventory should you trade to minimize the price impact? And in finance, they have some simple nonlinear equations to say, if I trade this much, here's the impact on the price. And then you just look at the sequential decision problem to say, what's the best fraction over time that I should trade at? Okay. Again, if I solve for the value function as a function of the trading fraction theta in the inventory, I find basically for low inventory at this end, I should just trade everything, right? It doesn't really impact my value. But for high inventory, if I do high trading fractions, they're really going to impact the price. So I really want then to have a low, a much lower trading fraction. I can look at the gradient with respect to theta, and basically I find, well, if you're going to trade at 0.5 for any inventory, it doesn't really matter whether you lower that 0.5 or increase it by a little or not. It's not going to change the value. If I'm trading at 0.18, a small change in that theta can really have a huge impact on your value, right? So this is sensitivity analysis. And rather than doing a lot of sampling, building a Pareto front, I can just look at these functions symbolically and just see everything that I need to know. Okay, one final point here is that often in SDP, a problem is that it blows up exponentially, especially in the nonlinear case. You can't simplify very easily. When we have fixed policies, when I observe your policy in the inverse RL problem, when I have a parametric policy, I want to trade a fraction theta, you actually get rid of the max. And the coolest thing we realize is that you actually get SDP that scales linearly with time and horizon. It's pretty unusual, but it means that when you have these problems with a given policy, SDP is actually easier than it is in other cases when you're optimizing a policy. So this is actually much more efficient than what I'm used to seeing in practice for SDP. So it's a very nice result. Okay, so finally, now I think you can go back to the talk title and realize why all these words are in there, right? I can take symbolic dynamic programming. I can take these parameterized hybrid MDPs with unknown parameters, right? It gives me really new possibilities for optimal decision analysis optimization that no one knew how to do before. Okay, so thank you, and I'll take questions.
Perhaps one quick question. I have a naive one. Mm-hmm. Imagine you represent your policy as a parametric policy. So after n step, you have your value function with the parameters that are the probability of choosing an action in a state. Mm-hmm. So could you use dReal then to optimize your policy in that way?
So you have a parameterized policy.
Yeah.
And you want to then solve for the the value and optimize the theta.
Yeah, the parameters are the policies of probabilities of choosing the actions.
Yeah, well, I think perhaps I wasn't clear, but it's exactly what we're doing here, right? We have this policy that says trade of fraction theta. We solve for the value function theta, and then we say, well, what? Now we can do R max over theta for an inventory and say, what was the optimal fraction?
Right.
Yeah. Yeah, so we can do global, no more policy gradient with local optima, we can do global policy optimization.
Yeah.
It's pretty cool.
Thanks. So, thank you. This was the last talk, and I have a